In this video, we're going to go over how applied stresses to equilibrium show up on graphs that are recording changes in concentration over time. So in other words, we're going to see how Le Chatelier's principle shows up on graphs that represent equilibriums. So at the top of this page here, we're given a couple of examples of what different stresses will look like on graphs. And all of these graphs, or all of these lines on these three separate graphs, represent the concentrations of either reactants or products. So these are all very helpful to keep in mind when we go through the questions. So for the first one, it represents a change that you'll see in the graphs when either heat is being increased or decreased in a system. Okay. For how to determine whether heat is being increased or decreased, it really depends on if your reaction is an endo or exothermic reaction. So based off of the information that I have in this example, because I don't know which lines are reactants and which lines are products here, I can't say for sure right now that if it's if heat is being increased or decreased. However, what you're looking for to tell you that heat is the stress being applied is all of the changes in concentration for your reactants and products. They are all going to be gradual changes. For pressure and volume, all of the changes of concentration when the stress applied is either a change in pressure or volume, all of the changes in concentration are going to be very sharp. Okay, so when I say very sharp, where I'm looking is right here. Okay, so there's either going to be a sudden increase or decrease, and if all of the concentrations suddenly increase, then that will tell you that pressure has increased. If you wanted to talk about volume here, just remember that pressure and volume do have an inversely proportional relationship. So that means if one goes up, the other one goes down. So if all the concentration goes up, that tells you that pressure has increased, or it could tell you that volume has decreased. Now, alternatively, if all of the concentrations go down, that tells you that pressure has decreased and volume has increased. And when I say all concentration go up or all concentration go down, keep in mind I'm meaning like all of the concentrations have increased quite sharply or decreased quite sharply. Okay, because that's the pattern that you're looking for, the sharp increase or decrease of all concentrations of substances to tell you if it's a change in pressure or volume. So if all concentrations go down, pressure has decreased, which means volume has increased. Okay, and then if the stress applied to the system involves increasing the concentration of one substance, what you'll notice on the graph is that one of the substances is going to change quite sharply, but the other substances are going to change for the last stress we can apply. That would be changes in concentration. So for changes in concentration, you're going to be looking for one sharp increase or decrease, and everything else is going to be a gradual either increase or decrease. Okay, so the substance that you notice has a sharp either increase or decrease, that is going to be the substance that the scientist changed. Okay, so for this example here, the scientist would have added some substance that binds to whatever ion that this concentration is representing, and that would cause the sudden decrease in concentration of the substance if you have an ion bonding or binding to an ion and it causes it to precipitate out of solution. Okay, so what that means is this substance bonds with another ion, which creates a substance which is insoluble in water. If you see a sudden increase in concentration of one substance, that means the scientist is adding more of that substance into the system. So what we've been shown in the example here is a sudden decrease in concentration. So the main idea is that whatever suddenly changes is what the scientists themselves changed. So that will tell you if the scientists either added something in or reduced the amount of some ion or some substance. So again, all of these three examples here are really useful for helping you to figure out what stress has been applied to a system at equilibrium. Remember that for Le Chatelier's principle, it's all about when you add a stress to the system or to a system at equilibrium, that equilibrium is going to shift in order to minimize that stress. And these graphs are recording the changes in concentration of the system of equilibrium before the stress is applied, when the stress is applied, and after. Okay, so we have an example. The following graph shows the concentration of certain substances as various stresses are exerted on a system. Points A, B, C, and D could be one of the stresses linked in the key off to the right here. So we've been given our equilibrium right here. It's an exothermic reaction. We know that because heat is on the product side here. All right, so what we're going to do is we're gonna first color code each of the lines just so it's easier on the eyes here. And then we're gonna look at each of these points, so point A, B, C, and D individually to figure out what one of these changes has occurred, and then we're gonna record our answers below. So we'll do chloride as blue, and I'll also color code that up here. We'll do our next one, oxygen, as yellow. Okay, and we'll do our last one as pink. Okay, so let's look at point A. So I'm looking at all of the shifts that occur. They all look gradual. So what that means is all of these gradual changes indicate that the stress applied is going to be heat. Okay, so that means I'm going to focus in on options 1 or 2. We're either adding heat or cooling the system down. So how we're going to determine which one it is we need to figure out, okay, what is increasing, what's decreasing. So it looks like chlorine and oxygen, they increase. So I'm just going to focus on those two. I'm not going to look at the product here just because it might make it a little bit more confusing. But seeing as our reactants increase, the only way that that can happen is if the reverse reaction is favored. And the only way that happens is if you increase the heat so that the system shifts away to use up some of that heat and produce chlorine and oxygen. Okay, so I'm going to say it's going to be 1, the addition of heat. All right, next one. So we're going to look at point B. All right, so let's see what's happening here. So all of these are a sharp increase. So that's going to tell you that either pressure or volume is being changed here. Okay, so looking at this, options 3 and 4 deal with pressure. So again, we've got to figure out what's happening with our concentration. So chlorine and oxygen, they increase, so does our product here. So everything increases, which means if your concentration increases, your pressure increases. Okay, so our answer is going to be number 3 here. Okay, so I'm going to actually write out what I've been saying just to capture it. And I'm going to do the same for point A. So all gradual changes, therefore, so that's what the 3 dots mean. The stress is heat. Okay, so point C, looks like we've got one sharp decrease and the other 2 are gradual, so that means that the scientists changed the concentration of oxygen here. So one sudden change, therefore our stress is going to be concentration. So if we look at our options here regarding the concentration of chlorine or oxygen, okay, so oxygen is the one that suddenly goes down, so that means that the scientists had to somehow remove oxygen from this system here. So that's going to be 6. So oxygen decreases. Okay, and then the last one here, point D. There's no changes at all in equilibrium. It remains at the same positions here. So looking at our final options here, we've got to pick the option that will not change anything. So we've either got the addition of a catalyst or the addition of oxygen. Okay, now since we have oxygen in our system, increasing the amount of it would cause the system to shift to the right. So you would expect to see more of your product or an increasing concentration of your product, right? However, if you add a catalyst or if you added an inert or noble gas, so just something from group 18, then that would cause no changes to equilibrium. So this one's going to be 7. Okay, and I just want to write a note underneath oxygen there. So oxygen is not a noble gas, therefore the addition of oxygen would change equilibrium or would cause the equilibrium to shift. All right, so that's that example there. So moving on, a graph can be used to represent the changes that occur when a system at equilibrium is upset. So in other words, if a stress is applied to a system at equilibrium. Okay, so we're going to talk about energy change effects on a hydrogen, nitrogen, ammonia system. Okay, so we know, looking at this graph, what is being represented here. So A, that's this area here. So it represents the initial equilibrium that the system is at. Okay, and at point B, that represents the stress being applied. And in this case, since all of the changes are gradual, that's how you know for sure that heat is being changed. Now, if we look here, we see that nitrogen has increased, so has hydrogen, and ammonia has decreased. But I'm just going to focus on nitrogen, just one side of the equilibrium, just to make it a little less confusing. So if nitrogen and hydrogen are being produced, that means the reverse reaction is being favored, and that can only happen if you increase the amount of energy. So right now, what we know is that the stress applied is that heat was added to the system. And now at point C and onwards, we have this new equilibrium being established. Remember, whenever your lines in your graph are parallel, that means that your system is at equilibrium once the lines are parallel. Okay, so right at point C is right when they begin to be parallel. So that is the beginning point of the newly established equilibrium. Okay, so everything underneath here just says what I said already. So moving on to pressure change effects on the hydrogen, nitrogen, ammonia system, we're going to fill in the blanks here. So we're given the option between the production or decomposition of ammonia results in a decrease in the total number of moles in a closed system. Okay, so let's just think about this for a second. Let's write out this equation. I'm just going to write it down below here, just so I can fit it all on the same page, or the same frame, I should say. And I'm just going to say energy. Okay. So what you're going to want to do, since we're decreasing the total number of moles in the system, let's figure out, okay, how many moles of gas do we have on the reactant side? How many moles do we have on the product side? So the total amount of moles on the reactant side would be 4 moles of gas. So I'm adding the 1 with the 3. I'm looking at the coefficients here. And then on the product side, there's 2 moles of gas. So if we're shifting to the side that has the lesser amount of moles of gas, that means that this equilibrium, as written, has shifted to the right. So that means if it's shifted to the right, the forward reaction is favored. Therefore, the production of ammonia is going to result in a decrease in the total amount of moles in a closed system. So therefore, either a decrease or increase in the total pressure of the system. Okay, so for this, we've got to think about what exactly is pressure. So if I do a little sketchy sketch here, we first got to talk about what exactly causes pressure. So I'm going to represent little dots to mean moles of gases. Okay, so pressure is created when moles of gas bounce off of the sides of the container that it's in. Okay, so if you have lots of moles of gas bouncing off of the side of the container, you're going to have a higher pressure. However, if you have less moles of gas, you're going to have a lower pressure because there's less moles of gas bouncing into the side of the container. Okay, so this is going to result in a decrease in pressure. So let's write out here beside this, less moles of gas equal less pressure. More moles of gas will mean more pressure. All right. When the pressure of an ammonia system is increased, so that's something we're actively changing or the scientist is actively changing, the equilibrium will shift to either decrease or increase the total pressure. So remember, for Le Chatelier's principle, when you apply a stress, the equilibrium will shift to minimize that stress. So if we increase the pressure, the equilibrium is going to shift to decrease the total pressure. And when we decrease the total pressure, the only way in which the equilibrium system can mitigate or kind of relieve that stress that's being applied is it's going to have to shift to the side with a lesser amount of moles of gas in order to relieve the stress. Okay, so in this case, we're going to be producing more ammonia. So just as a reminder here, when you increase the pressure, one of the ways in which you can increase pressure is by decreasing the volume of the container. Okay? So if you're decreasing the volume of the container, you don't have a whole lot of space. So the equilibrium is going to shift to the side that has less moles because there's less space to occupy all of the moles of gas. All right, so if we look at this graph of this system at equilibrium where a stress is being applied, so we start out with our initial equilibrium here, so in between points A and B. B is where a stress is applied. Now, since all of these are sharp increases, that means that it's going to be pressure or volume because all of the concentrations are sharp changes. And because they all go up, we can say that pressure increased. Okay, and how you can increase the pressure is by decreasing the volume of the container. So stress was applied at point B. So pressure was increased. How we can tell that is because all of the concentrations went up. And how this happened was because the volume of the container got decreased. Okay, so remember that pressure and volume are very closely linked. And remember, what happens to one, the opposite's going to happen to the other. Okay, so point B is where the stress is applied, and all of these kind of curves that come after the stress is the equilibrium shifting in order to deal with the stress that's applied to it. Okay, so at point C, that's where our concentration lines become parallel, so that's when you know that a new equilibrium has been established. Okay, so everything down here just states what I've already talked about here. So I'm going to add in here how we know that it was a pressure change is because all concentrations were a sudden change. So we know it's a change in pressure / volume because all concentrations have a sudden change. Okay, so there are some practice questions below here, so I'm going to move on to the next system here. So this is going to be talking about concentration change effects on the nitrogen, hydrogen, ammonia system. So how you can tell by looking at the graph that it's a change in concentration is where we look at point B, we only see one sudden change. That's your clue that you have a change in concentration. So the stress applied is that the scientist added more hydrogen into the system. Okay, we say that it was added because the concentration of hydrogen suddenly goes up. So stress applied is the addition of hydrogen gas. Okay, but in between point A and point B, that's the initial equilibrium. Then at point C and onwards, that's the new equilibrium. So with this addition of hydrogen gas, so it increases here. That's the stress that was applied. To kind of explain these changes here, remember that when you add something to a system, the system shifts away in order to use up that extra hydrogen. Okay, so what that's going to cause is it's going to cause the Ford reaction to be favored, which is going to produce ammonia. So that explains why ammonia's concentration goes up. And because, again, the forward reaction is favored, nitrogen's concentration decreases because it's using up nitrogen and hydrogen in order to produce ammonia. That's also why there's a small decrease in hydrogen after it gets added. It's because the system is trying to use up some of the excess hydrogen that was added to it. Okay, so again, everything that I said is written out right here. Now, I did want to go over this question together. So we have this system given to us here, and we're asked to draw an equilibrium graph to show the effects on the equilibrium of increasing the concentration of nitrogen dioxide. Okay, so because we are increasing the concentration, when we show the stress being applied, there's only going to be one line that has the sudden change. So because we are increasing the concentration of nitrogen dioxide, only one sudden change. The rest will be gradual. Okay, so let's find nitrogen dioxide. Okay, so I'll keep this line going here. So we'll try and do that as straight as possible. So here's where I'm going to apply the stress here. So since we're adding nitrogen dioxide, that means we're going to suddenly increase the concentration. So since we're increasing the concentration of nitrogen dioxide, the equilibrium is going to shift away from that. Okay? So what that means is the forward reaction will be favored. So for our gradual lines, nitric acid and nitrogen dioxide nitric acid and nitrogen monoxide are going to be produced as nitrogen dioxide, all of that, or not all of it. Nitric acid and nitrogen monoxide are going to be produced as some of this nitrogen dioxide gets used up in the forward reaction. Okay, so I'm going to just have this slope down a little bit to represent that this nitrogen dioxide is being used up. And then we're going to try and draw a straight line. Okay, that's as good as it's going to get. Now let's represent those changes in our other substances. Okay, so again, trying my best to do a straight line here. Now we said forward reaction is going to happen, so nitric acid and nitrogen monoxide are slowly going to increase. Okay, and then drawing a straight line here as straight as possible. And I'm going to do the same thing here. So just to capture what I've said here, the concentration of nitric acid and nitrogen monoxide increase as the forward reaction happens. And it happens because the equilibrium shifted to the right to use up some of that added nitrogen dioxide. Okay, so as the forward reaction happens, nitric acid and nitrogen monoxide are being produced. So we've got another pressure change effect on the hydrogen iodide system. All right, so we're starting off with our initial equilibrium. But then we have a stress added. So they all go up, so that tells us pressure increased. Okay, so because all of the lines are sharp, that tells you that the change is pressure. And because they all go up, that tells you that pressure is increasing. Okay, so that's likely due to the scientist decreasing the volume of the container, and then you have a new equilibrium established. Okay, but as you notice here, the wonky thing about this graph is that they all go up, and then they already immediately established an equilibrium right at this point here. Okay, so what's going on here? If we look at the balanced thermochemical equation here, we have 2 moles of gas on the reactant side, and we have 2 moles of gas on the product side. Okay, so what's going on here is that, like, when we increase the pressure by decreasing the container size, the concentration of all of the reactants and products immediately increase, and it's proportional to their coefficients in the balanced chemical equation. However, there's not going to be a shift in equilibrium because there's an equal number of molecules on both the reactant and product side. So as we showed here, there's 2 moles on the reactant side, 2 moles on the product side. So that's why there's no shift in equilibrium. Okay. So how you can tell that there's a shift in equilibrium is when you see these little curves that come after the stress being applied. That's the equilibrium shifting to minimize the stress that's been placed upon it.